So this video is going to be all about capacitance. So to introduce capacitance on a conceptual level, we want to think about a capacitor sort of as a spring for an electronic system. And what I mean by that is that in a mechanical system, a spring will store energy. In an electronic system, a capacitor will store energy. And so in order to see that, let's first draw two plates of a capacitor. So these are representing two parallel plates. And write down the relationship that that describes capacitance. And so capacitance, by definition, is some charge per electric potential. So effectively what this says is that if you have some electric potential that you set between two plates, the capacitance is how much charge you can put on those two plates given that electric potential. Okay, so to think about how this is like a spring, what we can do is we can think about adding charge to this incrementally and how that changes the potential energy. And so for some tiny little bit of change in electric potential, we can say that the tiny bit of change in potential energy is given by the charge that you have on the plate at some given time times the little bit of change that you're going to do to the electric potential. And so using this in conjunction with the definition that we have up here, what we can do is we can re-express this so that we say that V is going to be equal to Q divided by C, or dV is going to be equal to dQ divided by C. Taking this equation right here and then plugging it in right there, we see that du is going to be equal to Q dQ divided by C. Okay, and so now what we can do is we can integrate this so that we can find what the capacitance is. So we integrate both sides, and so we have the potential energy of a capacitor is going to be equal to 1/2 Q squared divided by C. And we can compare this to the potential energy of a spring, which says that the potential energy of the spring is going to be equal to 1/2 K x squared. So the thing to keep in mind here when comparing these is that you have something that's 1/2, you have something that's 1/2, you have something that's squared, you have something that's squared. The constant is different, but that same structure holds here, and this is one of the reasons why we can say that a capacitor behaves like a spring. Now, the next thing that we can do is we can actually calculate what the capacitance is for a particular set of conducting surfaces. And so in order to do that, let's lay out a framework that we can use for any type of problem that we see where we have to calculate the capacitance. So these are going to be steps to calculate capacitance. And so the first step is to find the electric field. Okay, and typically the way that we do this is via Gauss's law. So we have the integral of E dot ds is equal to Q in divided by epsilon naught. Second thing that we can do is we can find the change in electric potential by saying the change in electric potential is going to be equal to the negative integral from r vector 1 to r vector 2 of E vector dot dl. And the final thing that we can do is we can apply the definition of capacitance, which says that C is going to be equal to Q divided by magnitude of delta V. So what we'd like to do now is we'd like to actually see how this works in practice by considering an example where we have two parallel plates that are made out of cylinders like this. And we want to find what the capacitance of the system is. Now, what we'll do is we'll say that we're going to put some positive charge Q on here. This has some cross-sectional area of A, and these plates are separated by some distance of D. So in order to do this, we're going to first start with finding the electric field by applying Gauss's law. So step 1, we have the integral of E dot ds is equal to Q in divided by epsilon naught. Anytime that we apply Gauss's law, it's always a good idea to draw a Gaussian surface. And so the Gaussian surface that we're going to draw is partially on the inside of this conductor. And it extends out into the middle between these two plates. Now, when we want to find the integral of the flux through the closed surface, we also want to consider here that the electric field as an idealization is going to just point from left to right. In practice, you would have some field lines that go like this, but we're going to ignore those for the approximation that we're doing. And what that allows us to do is it allows us to calculate the flux through these three surfaces. So we have ds1, ds2, and ds3, like this. Now, this integral is going to reduce just to the integral over ds1 because E and ds1 vector are going to be in the same direction. ds2 vector is perpendicular. ds3 vector doesn't have any flux because it's on the inside of the conductor. The electric field is 0. So this says that the integral of E dot ds over this closed surface that I've drawn here is just going to be E times A. Okay, because when we add up all of the ds1, we get the whole cross-sectional area that I have here. Okay, this is going to be equal to the charge in divided by epsilon naught, which is just going to be the total charge capital Q divided by epsilon naught. And we can rearrange this so that E vector is going to be equal to, this is going to be equal to Q divided by epsilon naught times A. And to make this a vector, we'll say that this is going to be the positive x direction. So there's our step 1 complete. Let's look at step 2. We want to calculate the difference in electric potential between these plates. So delta V is going to be equal to the negative integral E dot dl from r vector 1 to r vector 2. And this is going to be equal to negative integral from 0 to d of q divided by epsilon naught a x hat dot x hat dx. This is just going to be a constant here, so the integral is rather straightforward. This says that this is going to be q divided by epsilon naught a times d, and the magnitude of delta V is going to be this without a negative sign. Okay, so that's step 2 out of the way. Step 3 is just to say that the capacitance C is going to be equal to Q divided by the magnitude of delta V. And so here this is going to be Q divided by Q D divided by epsilon naught A. We can cancel our Q's and invert the denominator. This ends up being epsilon naught A divided by D. And so you might remember, if you've taken a physics class in the past where you just use equations from an equation sheet, that this is the equation that you might have seen already for capacitance. So that's going to be it for the capacitance video. The next video is going to be all about resistance.